Welcome back to Applied Materials and Corrosion. Today we're going to think about some of the more interesting things that can happen at the surface of an electrode. So starting from our usual state that we've taken a, whoops, I haven't labeled my axes. Let's try again. So if we increase the voltage on our electrode, we can see that at some point our reaction will happen, whatever the reaction is, and it will increase to a certain rate and then stop increasing. That is because, to recap, at the surface of our electrode, the concentration of the reagent has gone down to 0. And in solution, the material going to the electrode can't get there any faster than the fastest rate that it can diffuse there. That's because it doesn't matter what the voltage is on our electrode. The other ions in the solution hide the voltage on the electrode by going close. So if we make the electrode positive in this case, maybe we've got a negative ion we're going to react. So the negative ion is going to come to the positive electrode, give it some electrons. That's our current. But if we make the electrode more and more positive, some other negative ions in the solution go and hang around near the electrode, and our target ion further away, our target cation that's positive, doesn't feel any higher voltage, and so it isn't motivated to go there any more than it would be normally. So therefore, once we've reached the highest rate that we can get to with diffusion, it's very hard, not impossible, but it's very hard to increase the current. But what happens if we increase our voltage faster? If we do that, we can possibly get to this point before the concentration reaches 0. So if we do that, something else will happen. So if we imagine a new experiment where we take our voltage here, where nothing is happening, and we step out to here, we switch suddenly to a voltage out here, then the situation will be like this when we start. The concentration next to the electrode will be the same as the concentration far away. It's the same concentration as the reagent in solution. So it's way higher than it would be in this situation. Let's draw it. So I've put a dot on the graph now for the current that we would see if we step there immediately. And then what we would expect to happen is the current would drop as we wait. So the current would drop in time, eventually down to this level, because this is the rate that would happen if the concentration near the electrode goes down to 0, the diffusion limiting current. If we go up in voltage at a normal rate, so at a realistic rate between infinitely slow, which is this one, and infinitely fast, which is jumping up, and then we see a current going down, we will see something in between. So let's draw that. Looking at this, what we can see is what we would expect to see if we had a concentration of something in solution that will react at our electrode, and we're changing voltage over time at a constant rate. We would expect the current to go up past where it should go, this point, the diffusion current, which is determined only by the concentration. It will go past it and then come back down again. So we can make this peak bigger, although it moves it slightly, by increasing the scan rate. And what we can still see, if we carry on our voltage for far enough, we can still see the diffusion current, which is a useful measure of how much stuff we actually have in solution. To explain anything any further, I think we ought to look at what is actually happening close to the electrode in all of these situations, and we can explain a little bit more why the ions in the solution don't move faster towards the electrode as we increase the electrical voltage. So for that we need an example. So here's my example. We've got hydrogen ions interacting with a platinum electrode, being reduced to hydrogen gas, H2, at the surface, and there's sodium chloride in the solution. So we've got hydrochloric acid with a bit of sodium chloride in it, and we can see what happens. So if we look at this, we can see the electrons can come down. I shouldn't really say CO so much. The electrons come down, they jump onto a hydrogen ion, and it generates a bond to the surface. and then this hydrogen bonded to the surface can find another one and be released as H2. But that's not the whole story. If we make this negative, sodium ions will come up and sit close to our surface. So if we draw the potential and the ion concentration, we can see more about that. So if we look at this graph, I haven't labeled the axes very well because I've got too many things going on. This is distance x away from our electrode. Close to our electrode, or let's start with far away from our electrode, the concentration of sodium ions and chloride ions are identical because we put salt in there. So that's the red and the green here, which you may or may not be able to see, but they're on top of each other. As we get close to the electrode, it's negatively charged, so the chloride ion concentration is lower. They're pushed out here. So here it's slightly higher than it is up close. It's slightly higher than equal, but it's spread out over a large area, or it's on the other electrode. Here we've got more sodium ions close to our electrode because it's negatively charged. We've got more sodium ions close to our electrode than we have in the solution. And that makes this area net positive charge, which means that our voltage, instead of decaying slowly with distance, which it normally would with the square of the distance, it decays way faster in an ionic solution. That means that our hydrogen ions can only feel the voltage when they get inside this area here, where there is a voltage compared to the solution. Once they're outside here, they're just moving under diffusion. So how thick is this layer? It can be very thin indeed. If we scan very fast, so we've used up only the electrolyte very close to our electrode, this can be of the order of nanometers. If we have a low concentration and we change our voltage very slowly, it can be much further than that. It can be up to millimeters. So the current that we actually measure is determined by the ions that we're interested in diffusing through this thin layer close to the electrode if we're measuring at diffusion limited current. So if we're measuring at a voltage that's high enough that the ions can only get there by diffusion, we can assume that the concentration near to the electrode is 0, and the concentration out far away from the electrode is the concentration that should be in there. And in between there's some kind of drop, which is driving the substances towards our electrode. But because that can be slow, as you might expect, if you've made density cocktails where you pour sort of a stronger sugar solution on the bottom and a weaker and weaker one, you get layers of drink in your cocktail. It's pretty horrible usually because they're chosen for their density and maybe for having a pretty color and not because they taste nice. They take a very long time to mix, and they're mixing by diffusion. So from that example, we can imagine that diffusion is going to be comparatively slow because the distance isn't very far. It's not that bad, but it's relatively slow, which means that if we do this in a beaker, so the ones that I've been doing so far, with my electrode in a beaker and a piece of paper into another beaker with another electrode doing the rest of the current. If we do that, the current will not be caused by diffusion at all. It'll be caused by me stirring by accident or something falling in. Maybe it's a bit warm on the bottom, so there's a convection current, and all of these are called convection. So the current that we will actually see will depend on convection, and it will wobble around a lot. But for the time being, we will worry about what happens close to the electrode. So looking in closer to the electrode, we can see in some cases, so I've changed my electrode to silver now, and at the surface of silver you would imagine that the chloride ions would love to stick to it because silver chloride is a very stable solid. If we have a layer of chloride ions at the surface of the silver bound to it, we would have a lower voltage, more negative voltage, than we're actually thinking that we've put on there, because we've got lots of negative charge, And then outside that, obviously, because it's very negative, there will be more sodium ions and less chloride ions. And so the voltage will come back to close to zero. That means that our electrode has a thing called a double layer on it. The first layer being adsorbed ions and the second layer being a decay function of the voltage, depending on how many ions we've got in solution that are getting in the way, that are interfering with voltage getting through to the outside, with the field affecting the liquid out here. In some cases, the apparent voltage close to the electrode is actually the opposite of what we think the electrode is. So if we make this silver electrode slightly positive by taking electrons away, it would still be negative compared to the solution because of the chloride ions attached to it. So if we take our voltage and we sweep it in time, so we change the voltage linearly with time, in this case we're making it more and more negative until the hydrogen is reduced at the surface of the metal, and then we pass it a bit, then we come back, we will see something interesting. Let's build it up as if there weren't any hydrogen ions in the solution to start with. So as we go more and more negative, we're going to cause sodium ions to come up close to our electrode. Eventually we're going to cause those chloride ions close to the electrode. Some of them will leave because we're pushing them away. Then we get to our most negative part. Then we come up again and we're causing the sodium ions to leave again, and maybe some chloride ions to come back, because if we go positive, we're obviously going to have more and more chloride ions here and less sodium ions. Exactly the opposite as before. Effectively, the ions in the solution will shade the electrode potential from the solution if it's positive or if it's negative. And if we're changing, it will switch from one to the other. So let me draw just a negative case because that's our one. So this is our situation at the bottom here somewhere. We've got sodium ions close to the electrode and negative charge on the electrode. And as you can see, what you might be able to see, as you can see, it looks very much like a capacitor. We've got positive charges and negative charges next to each other. So that is a way of storing charge. And as we go back the other way, we will move the ions away. What you can also see is that if I change it over, flip it to the situation here, where we've got chloride ions close to the electrode and positive charge on the electrode, so holes where there would have been electrons, you can see that some current has flowed without actually doing anything to the solution. It's not very much current, but some current must flow in order to charge up this double layer, this weird type of capacitor. If we do this experiment, we would find, we can't really do it with hydrogen, but if we do this in other cases, we find that we can charge the capacitor up and the current flows, and the current is dependent on how fast we change the voltage. So there is a disadvantage to sweeping the voltage faster. The faster we sweep the voltage, the more current we get from this effect, which we probably don't want to measure. Remember, this was the shape of the curve that we would get normally with our reagent, so we need to add that to the shape of the charging the capacitor curve depending on what we get. So I'm going to add that to it now. You notice that we were going up and down with the voltage, positive and negative, so now we will see what happens when we come back. But obviously, because this peak comes from, it's not very smooth, but it's normally smooth, because this peak comes from having a higher concentration in the solution than the diffusion coefficient controlled case would show. So close to the electrode, the concentration hasn't gone down yet because we moved our voltage too quick. If we come back, we can't have that because we've already passed the maximum current. We're back to the diffusion current, the difference between here and the extension of this line, not very much in this example. So on the way back, we won't see that peak. So there it is with no peak on the back sweep. But however, we have generated some hydrogen gas dissolved in the water close to our electrode, and the hydrogen gas can react. The moment it gets positive enough, the moment the electrode becomes positive enough, the hydrogen gas can give its electron back to the metal, and the reaction can go in reverse. This particular reaction, hydrogen turning into protons in the water, is perfectly reversible, so we would expect to see a peak immediately after it. So we would make hydrogen here, and we would use the hydrogen back up on the way back. Obviously, if we scan very, very slowly, we would see a step here instead, and on the way back we wouldn't see this at all, because the hydrogen would have escaped in the time that we were going back very, very slowly. So quasi-infinitely, this would be just a step. You wouldn't see the capacitive current, because the slower you change the voltage, the less current effectively you get from the capacitance. But you wouldn't see this peak either. You would just see a step, and then on the way back you wouldn't see a return peak, because there is no hydrogen to oxidize. So now we get to something that might be a little bit difficult to understand, so let's take it slowly. If we take platinum, we know it's a catalyst for hydrogen. So platinum we would use as a hydrogenation catalyst for things with double bonds. So if we want to make margarine out of oil, like they do near to us, we would take platinum, a platinum catalyst. We would take our oil with double bonds in it, olive oil for example, and we would bring hydrogen up to it. The hydrogen sticks to the surface as singly bonded hydrogen, and it can interact better with a fatty acid molecule from the olive oil than it could if it was in the hydrogen state. That's because this bond effectively is broken in half, and the activation energy is half as big for the whole reaction, because our hydrogen is already broken. We've still got to break these bonds, but we've only got to break one at a time, whereas normally we would have to break both at once. If we use palladium, it doesn't work as well. So if we use a palladium catalyst, the bond to hydrogen is excellent. It's way stronger than the bond to platinum, between platinum and hydrogen. The bond between palladium and hydrogen is stronger, but there's a problem there, because although the hydrogen breaks very easily, it's hard to get this hydrogen back off again, and so this isn't as good a catalyst as platinum is. We could make it weaker. So if we take an iron catalyst instead, we can make it weaker, but then the bond is to the iron is very weak, and that means not very much of the hydrogen will break into hydrogen single atoms stuck to the iron. Most of it will hang around as a gas, and so it's not a very good catalyst either. Platinum just turns out to have a similar bond strength to hydrogen as hydrogen does to itself. So 2 of these is equal to 1 of these. Why does that matter here? If we take hydrogen, we can do this measurement, and we see that these peaks are very close to each other. That the difference in voltage between making hydrogen and using up the hydrogen to make hydrogen ions is very small, and so this part in between is pretty much non-existent. The 2 peaks are over the top of each other. That would be what we would see. If we take any other metal, we see typically that the making hydrogen is slower. It's more difficult to make hydrogen on another metal, because the activation energy between making a hydrogen atom stuck to the surface is a lot higher. So if we do this experiment, what we see is, for a reversible reaction, there is very little difference in voltage between the forwards and reverse peak, between the reduction peak and the oxidation peak of the hydrogen. But if we do it on a different metal, where it's more difficult to make it, where there's a much higher activation energy, we get an overpotential. Let's see what that looks like. So this would be a metal on which it's harder to make hydrogen than it is on platinum, because the hydrogen has a higher activation energy and that shifts this reaction out. So looking at these values from Wikipedia, we can see if we take hydrogen formation from water or hydrogen formation from weak acid, that should happen at about 0 volts. We shouldn't be able to make our electrode negative in acidic water. If we take a platinum electrode, we can't. It is a little bit difficult too, so the overpotential, the extra voltage that we have to put in on a platinum electrode to form hydrogen is about 0.07 volts. So we have to put in a little bit of extra energy. But look at how much we get from carbon, 0.62 volts, so we can go down 0.62 volts before hydrogen forms. And if we go to mercury, which is the usual element that used to be used historically for doing electrochemistry at negative potentials, the reason for that, there are two reasons for it. One of the reasons is that we can get down to minus 0.85 volts before we make hydrogen, in addition to whatever we get from reducing the concentration of H+. So obviously if we do it in a weak base solution, we'll have a lot less hydrogen plus, a lot less protons in there, so that will move this voltage down, and then we could get further than this. If we go up to oxygen, we will see the same effect, but obviously the metals that make it difficult to form oxygen are not the same as the ones that make it difficult to form hydrogen, and the ones that catalyze the formation of oxygen are not the same as the ones that catalyze the formation of hydrogen. So to sum up, if we look at an electrochemical process, a redox process that we're going to do in solution at one of our electrodes, we can see that the position where it occurs is determined just by the thermodynamics of the process. However, there is also the activation energy, G, which will shift the two half reactions apart. So just concentrating on the overpotential at the electrode, the electron transfer from the metal or carbon from the electrode to the solution, to the thing that we want the electrons to go to or to come from, is hindered by some kind of activation energy, and that determines the overpotential, which is the difference between the two parts of our reaction, the oxidation and the reduction. So to illustrate that, we will do a demonstration where we take a piece of tin dissolving in mild acid is strong enough, so the reaction is negative enough that it could cause hydrogen to form. However, the overpotential of hydrogen on tin is quite high, and so it is very slow and doesn't happen very much at all. So we take a piece of tin and throw it into hydrochloric acid and nothing happens. The tin is reasonably stable because the hydrogen can't form on the surface of the tin because of the activation energy. If we take another metal, copper or platinum in their examples, and we attach it to the tin, then we will see that hydrogen forms on the copper and the tin dissolves. That's because the whole metal block is pulled to the voltage of the tin. The hydrogen forms on the copper because it can form on there easier because the overpotential is lower, and the tin dissolves. This is an example that brings us closer to our title, because this is a type of corrosion effectively. The oxidation is all happening on the tin, and the reduction is all happening on the copper. There isn't any formation of anything solid because we're forming hydrogen gas, so this should bubble and this will dissolve. We may or may not see the tin dissolving, but we will see bubbles forming on the other electrode, and that's just because the overpotential of hydrogen on tin is so high that we won't see it in the concentration that we choose. So I'll look for a concentration where hydrogen doesn't form on tin, so that we can see the difference when we connect a piece of copper to it. I'll try to do it without too many cuts so that it's the same solution. In closing, we've looked at three things today: cyclic voltammetry, double layer, electrical double layer, and overpotential. Each of these things has a Wikipedia article. Let's have a look at those for just quickly. This is the Wikipedia article for cyclic voltammetry. You can see the diagram that I was trying to draw here, and it has a long explanation. Some of it is a little bit complicated, but it's not too bad. So we've got voltage going up, coming back down again. In this case, it's starting at negative and going positive. We started positive and going negative. So here we are, negative, positive, negative, positive. We can do as many cycles as we like. This is what it would look like in time, and this is what it looks like if you plot it voltage against current. This is the Wikipedia article for the double layer. In their case, they've got positive ions stuck to the surface in this first diagram, and negative ions attracted to them. Far away from the surface, there is no net charge because the positives and the negatives have balanced out. If we go down to here, we can see a diagram of the potential against the difference and how it decays very quickly as we get further away from the electrode. Most of the charge is gone within a few atomic radii. And then there are a whole lot of models for how we can describe this. This is the Wikipedia article for overpotential. You can see it gets involved very quickly. Apart from this table that just has pure values that say how much different the voltage is compared to what we would expect. So for hydrogen it would be 0 on different metals. Apart from that table, I haven't really mentioned much.